This is a lesson on intensity and energy of light in a unit on light and optics. To review a little bit, waves carry energy. That's the point, the fundamental purpose of a wave. And waves expand radially from their source. We're going to remember that as we think about energy, that energy is going to expand from the source radially, and keep that geometry in mind. As such, the energy of a wave is distributed evenly over the surface area of a sphere. So I put the surface area of a sphere down here. Here's the equation. And so the sphere gets bigger and the total energy gets distributed evenly over an ever increasing surface area, which makes sense for us as human beings on the surface of a planet. We know as we get farther away from something, it gets less hot or less bright, right? Another principle to review here is intensity. It's the measurement of the density of power that passes through an area. And so I have that equation over here, power over area, and we'll be using that equation as we move into light. One thing I wanted to introduce or review as we're moving more towards looking at the electric and magnetic fields in a light wave is root mean square values. And I think root mean square values are kind of nebulous if you don't understand where they come from, but they make complete sense once you do. And so that's why I'm taking a moment to explain it. For quantities that oscillate value in time, such as a sinusoidal function, you cannot find an average value by just using the standard average. Because if you look at the average value of like this magnetic field over a cycle, the average value is 0. So it doesn't help to average it. And then so what do we do? How do we find an average? And so what we do, the strategy is to square the function. And when we square a function, all of the negative values become positive. So I'm going to put this over on. So if I take the magnetic field and I square it, the positive, I'm going to get a little bit larger value. But when I look at the negative, I'm going to square the negative and it becomes positive and the same height. Once I've found the squared value, what I can do is actually find the average of the squared value. Once I have the average of the squared value, it says take the mean of the square of a function, then square root to undo that initial square that we did. Okay, so that's why they call it a root mean square. We square it, we take the mean, and then we root it again, root mean square. And that's what it means, is just the average. So in your head, when you're thinking about it, this is the average value, but it is a root mean square value. We had to do this strategy in order to find the mean of it. So when we look at the electric fields and the magnetic fields in a light wave, they oscillate with time, and we would be interested in the average value of that. What's the average value? The maximum and average values of these electric fields are related to one another. So if we wanted to find the RMS value, we would take the maximum value and divide by root 2. And the root 2 makes sense. If you square something and then take the mean of it and then take the square root of the mean, you'll get a root 2 out of it. So that's the root mean square. I'll be using these equations as we move forward, and they are available to you as you're working on homework or etc. So that's the idea of root mean square values. And what we're going to do is relate these values to the Poynting vector. We've already covered that the electric field and the magnetic field are related to one another along with the intensity. Remember, intensity is a measure of energy. So we're getting this relationship between the fields in an electromagnetic wave and the intensity of that light. We're going to remember that the electric field and the magnetic field are a constant ratio over each other. So Emax over Bmax is the same ratio of Brms over RMS, is the same ratio of the electric field at any given time over the magnetic field at that same time, those two values. Without getting into Maxwell's equations and deriving the equations, what I will tell you is that we will look at the energy density of electromagnetic waves. Energy density is given, and I'll point out the units down here, joules per meter cubed. So it really is a density of volume, like you would think of density, but this is in terms of energy. And since the electromagnetic fields carry energy, we're interested in quantifying it. that energy density is related to these fields in this way. And I'll point out the last part of this equation. I could have arranged this equation differently, but I find that functionally, practically, you will use these two versions more frequently. But the main idea here is that there is energy in the electric field of a light wave, and there is energy in a magnetic field of the light wave. And we know this when we first studied capacitors. We know that there's energy in a capacitor. Also, when you study inductors as a circuit element, just like a capacitor is a circuit element, an inductor is a circuit element, we know that there is magnetic energy stored in the inductor. And so we're not surprised to see that the energy density of a light wave, which has an electric field and a magnetic field, have contributions to the energy of both of these fields. So that's the relationship here. What I'm going to say is that the contribution due to the electric field is equal to the contribution to the magnetic field. So this term here is equal to this term here. And when you simplify that, you could take 2 of this term and see that you get this value, or you take 2 of this term and you get this equivalency. So now we're able to relate the magnetic field or the electric field to the energy density of that wave. Okay? Let's tie in the last thing here. The last thing we need to do is to relate the intensity to this energy density. And there is a direct relationship here. The relationship is given by the Poynting vector, but in scalar form. And so this is what my professor at University of Illinois, Urbana-Champaign, Naomi Makins, called this the suck equation. And so we're relating the intensity to the energy density, and the speed of light is in here. So energy density has the electric field and the magnetic field, the RMS values in here. You could relate it to the maximum values if you wanted to. And that this intensity of the wave is related to the amplitude of these waves squared. Do you see that? If I increase these fields by a factor of 2, the energy will increase by a factor of 4, right? There's the squared in here that happens. Intensity is related to the square of the field. We have the speed of light in here. This is the standard speed of light. And again, this is the Poynting vector. It has units of intensity, which is watts per meter squared. So you'll be using this intensity as you would when you studied energy from waves with sound waves, etc., when you first learned that material. And so we're going to carry along the intensity equation, power over area, along with all of these other equations. And so I picked a couple of examples just to get used to using these concepts and looking at the magnetic and the electric fields in light. And so we're going to carry along the intensity equation, power over area, along with all of these other equations. And so I picked a couple of examples just to get used to using these concepts and looking at the magnetic and the electric fields in light. So the first light wave that I've chosen for us to look at in this regard is the cosmic microwave background. And this is sort of a relic of the Big Bang. I'll read the problem here. The microwave radiation left over from the Big Bang explosion, so there was an explosion and a bunch of light was released, and it's a microwave. This is microwave radiation. In the cosmos, it's just in the background, just ambient in the background, has an average energy density of 4 times 10 to the negative 14th joules per meter cubed. What is the RMS value of the electric field of this radiation? So this is the average energy density. I can say U equals 4 times 10 to the negative 14th joules per meter cubed. Okay, it wants the RMS value of the electric field. So when I look at the electric field, I can see that the energy density is related directly to that electric field. So I can set this equal to epsilon naught ERMS squared over 2. So I'm going to solve for ERMS. ERMS equals the energy density divided by epsilon naught and square root. So I can plug things in here, 4 times 10 to the negative 14th. I'm going to divide that by epsilon naught, which is 8.8542 times 10 to the negative 12th. And there's some constants in there. You can work those out for yourself if you'd like to. and I get the average, the RMS value of that electric field due to that microwave background to be 0.06721, and the units of electric field are newtons per coulomb. And so that's the average value, which is not a lot. I like doing this problem because it kind of gives a base about electric fields in light that we can be familiar with. So the basic one is that there's a background due to the Big Bang, and that's the electric field from it. The next problem I chose is a light bulb, and so we can compare the electric field due to that background due to the electric field of a light bulb. A light bulb emits 5 watts of power as visible light. What are the average electric and magnetic fields from the light at 3 meters from the bulb? Okay, so we have the power. Power equals 5 watts. And I know intensity is power over area. I have that over here. So I can relate the intensity. Remember that intensity is the Poynting vector. This is actually an I value. I can relate the power to the intensity and the intensity to the energy density, and then the energy density can give us these fields here. So that's sort of what I'm thinking in my head. So let's keep solving. I equals power over area. I'm going to put a UC in here for intensity. Remember, intensity is the Poynting vector, and the Poynting vector is UC, and that's power over area. I'm going to put in what I know for U. U, in terms of the electric field, epsilon naught ERMS times squared, and that is still multiplied by C, and that equals power over area. I'm going to go ahead and solve this for ERMS. ERMS squared equals, let's see, I have the power over epsilon naught C times the area. One thing I'm going to do here, you can plug in epsilon naught and C. I guess that's not too big of a deal. The power is 5. Epsilon naught is 8.8542 times 10 to the negative 12th. The speed of light, you can put in 3 times 10 to the 8th. I like being more exact, so I use the exact value here. And then the area here is a sphere of 3 meters. So the surface area of a sphere is 4 pi r squared, so I have 4 pi times 3 squared. If I want to find ERMS, I have to square root this quantity, so we'll square root around it. And ERMS turns out to be the average electric field of the power that comes out as visible light from the light bulb is 70,000 newtons per coulomb. So here's the value for it, 71,000 newtons per coulomb. So that is the value. Remember, on the microwave background, it was 0.07. Here we're many magnitudes of order larger than that. So that's why it would do damage to our eyes. If we get too intense of a light, this electric field would get too large, and that's what damages our eyes. There's too much energy coming into our eyes, and it damages our receivers. So we also want to find the magnetic field. The magnetic field shouldn't be hard. I can use this equation up here, C equals E over B. I can solve it for B equals E over C, and this can be the RMS values. Remember, if I put the max in here, I would use max, but since I'm looking for RMS, I will use RMS. So I would just take this electric field and divide by the speed of light. So I have it written there, and when you do this, when you run it through the calculator, you get the RMS value of this magnetic field to be 2.357 times 10 to the negative 4th Tesla. So less than millitesla. It's a pretty small field. But remember, the ambient magnetic field due to the Earth is usually around 5 times 10 to the negative 5th Tesla. So this is the Earth's magnetic field. So it's larger than the Earth's magnetic field, and that's the magnetic field that corresponds to an electric field of this value for light traveling through a vacuum.